This is a production of Cornell University.
Thank you, Nate. The first thing I want to tell you is it's very edifying to come to Cornell. And if you're a young student, you can look up the word edifying, but it means spiritually enlightening. And that's one of my favorite words. Lots of things in life are edifying, including coming here. Right out of the gate, I want to tell you, this is unique because I'm honored that Bob Langhans is with us. He's come from way out of retirement to be here. Bob was real influential in my early career. I was never a student here, but he would comment on the talks I gave, and he inspired me to attempt great things. So Bob, I appreciate that. This was 40 years ago now that we're doing that. And it says something about a department when you have emeritus faculty that are still part of the department, that kind of enterprise is bigger than any one person. So of the many things I might have talked about, I chose to talk about this title right here. And this is mainly because this is poorly understood. And I want to help shed a little light on this subject. I'm also inspired to talk about this because another influential person in my life was Lou Albrecht. And many years ago, he and I would compare notes. I was funded by NASA, which is growing plants, indoor agriculture on Mars, and what's the cost effectiveness of that? And Lou was doing it here on Earth. And he was another influential person in my early career. So I understand that this is the graduate student seminar. So I'm going to take the opportunity to do a little more philosophy than I might have. And my very first picture is of an artist. This is Henri Matisse, the French artist. And he is famous for this quote right here. I don't paint things, I paint the difference between things. And it was a number of years ago I read this, but it just hit me hard. In science, we're always trying to do absolutes, and absolutes are very hard to do. So we do relatives. And much of what we do says, this is bigger than that. Now I'm going to tell you it's 12% bigger, but I'm not sure about the 12%. It's just bigger. And it helped me get a perspective on what we can do in research and what we can't do. And much of what I'm going to show you is relative. This is bigger than this. This is a difference between things. And we do the best we can to get absolutes. But that was a influential quote in my life. Now, here's wheat in the field. I have been an active member of the Agronomy Society for my whole career. And in fact, I've gone to more agronomy meetings than I have at horticulture meetings. And look at how people focus on agronomic crops, corn, soybeans, wheat, just exceptionally well studied. Hundreds of people studying this. So we can take the models that we've used for wheat, the many models, and wheat, by the way, is what we've been funded by NASA, early in my career, funded by NASA to study wheat in controlled environments, and apply those to now on Earth, controlled environments, and wheat without sunlight. So I want to acknowledge two funding sources. I've been funded by NASA pretty much continuously through a 40-year career, and it's really been helpful, and it's competitive proposals, but I know what their needs are, and I'm able to write proposals that have kept us getting funded. It's been a remarkable thing for me. And now in recent years, we've been funded by USDA. And Neil here, Madsen, is also funded by this same group. We call this the LAMP project, Lighting Approaches to Maximize Profits. So this doesn't say indoor ag, it just says electric lighting. So with this background, I want to go from the field to indoors and look what we can do. Now, Henri Matisse painted pictures. He didn't put text, he didn't put equations, he painted pictures. And the more I do this, the less I try to use less words and less equations and more pictures. And the pictures can be, and the graphics can be memorable. And if there's one thing I think I'm finally starting to get good at in this point in my career is more graphics, and because they're memorable. I know it is, because I've seen my own students take graphics I made and give talks 20 years later using the same images. If I would have put words and pictures up, they wouldn't remember them. So I'm going to try and show you the physics of farming without sunlight in graphics. We're going to start with 100 years ago, agriculture. Pretty simple. We used a lot of animal agriculture, a small plot, the rain came in, and we got some yield. Now we vilify animal agriculture now because of the way it's done in developed countries, feedlots. That is real inefficient. We try to get people to change their diet. That's part of what my TED Talk is about. The TED Talk is called turning water into food. But it's an appeal to people to change their diets to save the planet. But when third world countries do animal agriculture, it's really efficient. They feed the scraps. The animals eat on land that can't be used by people. Animal agriculture is not bad. It's just the way it's practiced in the United States that causes problems. So there it is, small yield, rain-fed. Now we fast forward to today. The same single farmer grows a much bigger plot of ground. The yield is much higher. And by the way, all these arrows and these things are scaled to inputs and outputs. The size of the arrow is the size of the inputs. But now we rely way more on groundwater and fossil fuels than we ever did. And 30 years ago, we were being criticized for fossil fuel agriculture, but fossil fuels are cheap. That same grower grows a big expanse of ground, especially in a place like Utah. We rely heavily on irrigation. We use a lot of groundwater. Lots of evidence we're going to run out of water before we run out of fossil fuels. In fact, compelling evidence we're going to run out of water for agriculture. So there it is today. Yield is bigger, same person. Now, if I told you the arrows are scaled to inputs and outputs, the pixels in this green arrow are bigger than the pixels in that black arrow. The first law of thermodynamics says energy in equals energy out. So how can this be if we have this much energy in? How can we get that much energy out? Doesn't this violate the first law of thermodynamics? No, because we forget about the elephant in the room. Kaboom. 60 moles a day of solar radiation coming into this. This is a bright, sunny day. And you know how crop production is maybe 2 or 3% efficient? Well, that's 3% of that. This becomes insignificant when we think about the massive input of solar energy. So we know what the efficiency of LEDs are. They're astounding. And we've got a bunch of papers on where they are, where they're going to get to. What if we wanted to give a field electric photons from LEDs and we paid the electric bill? What would that cost to do that? It's $500,000 per hectare per 100-day growing season. And you think about the value of agricultural land and you realize people are buying sunlight. They're buying a surface area with free photon input. That's largely determines the value of our agricultural land because the sun comes up for free. But this is 50 cents per meter squared per day. And you think about $500,000 per hectare, big inputs that would be very expensive to replace with electric lights. Now this is full sunlight to get this. So if we take that out of there, oh, now you put this little sidebar in. I told you I wasn't going to show equations, but this is arithmetic. So, and I want to show you how we get this because it's really pretty easy to calculate that number. This number right here is what we call the efficacy of electric lights. Now, efficiency would be watts out and watts in, but photosynthesis is not driven by energy, it's driven by photons. So the numerator has to be photons, and the input then comes out to be joules of electric energy. And people that are in this business know this number. And high pressure sodium lights, which were the gold standard in the recent past, are 1.7 micromoles per joule. And that's even with some advances. This number is double that. So it's just an astounding increase in the efficiency of lighting. We're up to close to 70, 80% efficient of LEDs now. I mean, it's incredible. There's the efficiency. This is 10 cents a kilowatt hour. It's a standard price. A kilowatt hour is a really bizarre unit. There's power, watts is power, joules is energy. A kilowatt is a joule per second. A kilojoule per second, hours is time. A kilowatt hour is 3.6 megajoules when you do the math. So we can buy 3.6 megajoules of energy for 10 cents. Now the beauty of this is 10 to the minus 6, and that's 10 to the plus 6, and that cancels, and you got to multiply 3 by 3, divide by 10. 120 moles of photons for $1. Now this is very state-of-the-art LEDs, but that's an amazing number to remember. Not so long ago, this was 100 moles per $1. And in fact, this is a bit futuristic. We're not here yet. But that means a mole of photon costs a penny. I should write that down on the board somewhere. A penny per mole of photons. Wow, does that simplify the economics? You need 30 moles a day per meter squared per day for your crop. That's 30 cents a day. When you run that number, you can do a lot of math in your head. So it comes to this. And now, if full sunlight, bright sunny day, 60 moles of photons per meter squared per day, times this right here, multiply two numbers together, there's our numbers that I just showed in that slide. That's where this comes from. And this is a little futuristic, but that's okay. I mean, I think we're gonna be here in the next few years in terms of the efficiency of lights, but it's still a lot of money to buy photons produced with an electric light. So now we take the without sunlight part of this talk and we put a box around it. And this is the exact same thing, only with a box around it for indoors. Now, how do we make this balance? Fossil fuels for the electric lights. It's a massive input of electricity to replace sunlight. And when I do the math on this and I start to calculate exactly the efficiencies, this is a little too big. It could be a little smaller, just because electric lights are smaller and we can get lower intensities, but still the size of this arrow is big. So how do we run indoor agriculture given this picture right here? Well, a huge part of it is it's closed so we can elevate CO2. And that's universally done. If you're going to enclose it, that's one of the biggest reasons to enclose it is so we can elevate CO2. And that is associated with about a 30% yield increase. Photo respiration and all this stuff. Tim Setter was just in here teaching this stuff a minute ago in this class. It's about a 30% yield increase, but that easily pays for the cost of CO2. So cool. And like I say, we're working on this for the whole planet, trying to get CO2 up to make agriculture more efficient in the field. But so now we get that added efficiency, and that's part of the reason this arrow can be a bit smaller. But one of the common claims, in fact, not common, universal claims about indoor agriculture is incredible water use efficiency. You see the claims 1,000 times more water use efficient than the field. So what's going on? Are these plants got their stomates closed? They're not breathing? You know, how do they get this water use efficiency? Dehumidification. Plug in a dehumidifier, the transpiration rate's almost the same. CO2 closes stomates some. So it still goes to water vapor, but we don't let the water vapor escape. And on the earth it escapes and it blows back to the ocean and gets mixed with salt water. We trap the water vapor and condense it and put it back on the crop. So when you think about this, the water in this thing almost could come down to the water that's in the produce itself. No added irrigation, it's just recycled and recycled. What a wonderful thing. And if we're out of water, this is going to make a lot of sense. And now you're going to say, well, Dr. Bugbee, couldn't we just plug in a dehumidifier in the field? Yes, we could, but it takes a lot more energy when it's low humidity to do that. But we could literally take electric energy, condense water vapor out of the air and irrigate our crops, just not cost effective in the field. But it will be cost effective here when we run out of water. But guess what? It takes energy to run the dehumidifier. Boom, now we get fossil fuels to dehumidify the air. More energy input, but if water is more precious than energy, this makes sense. And it might well come to that. This arrow is smaller than this because we can use heat pumps and it takes less energy to condense water than it does to run the pure electricity for the lights. There's a lot of ways we can do this in a cold climate. You just run cold air through the pipes. So there's a model of where we're at with conserving water. And this is something I wish people promoting this would explain. There's nothing wrong with this. It's just that condensing the water doesn't come for free. It's not like the plants actually use less water. We just can capture it and put it back on the plants. So now, I've worked in this diagram a while, but people say, well, yeah, your big black arrows, we'll just use solar panels for those, and it's all good. And now the sun is electricity. So I'd like to take a close look at this. Can we use solar panels to run this farm? So this is sunlight, and here's our 60 moles a day, a bright sunny day. This is the quantum flux from the sun, moles of photons. The energy flux, the exact same sunlight, is 30 megajoules per day. Just two different instruments. One's measuring energy and one's measuring photosynthetic photons. And on this side, I'm going to show a greenhouse. And on this side, I'm going to show indoor farms. So we first take a greenhouse. And a design goal for greenhouses is 70% transmission. We don't always quite get to that, but we can with state-of-the-art. 70 times 60, we get 42 moles per meter squared per day inside the greenhouse. How close can we get with electric lights? Solar photovoltaics, the commercial versions, get up to 20% efficient. I have them on my house. They start at 19%. Now they're down to 17%, but they're still, we can get close to 20%. So that 30 turns into 6 megajoules of electricity per day. Now we multiply by the very best LEDs. 3.5, that's what I showed in the other slide. We're getting close to some purple LEDs that are close to 3.5 micromoles per joule. So this number, the mega and the micro cancel once again, and the product is 21. So if we take the same sunlight, run it through solar panels, run it through LEDs, we get half of the photon flux per unit area of sunlight. And this is even a little bit futuristic, half. So what that means is if we take 2 acres of solar panels, this is a picture off the internet, and it looks like really nice farmland, and they got solar panels on it, I'm not sure, but if we can run 1 acre of LEDs at full sunlight. This is not a really favorable ratio, but it does make the point when people make skyscrapers with 30 levels, and then the solar panels are on the roof. Oh, right. Those solar panels are going to provide sunlight. It's not going to happen. But when you think about this, this is full sunlight, and this is now. Now I'd like to take a look at the potential of this, not just what we have now, but what it could be. Same diagram. Greenhouse is the same. Now maybe it will get better coverings. Maybe this number will go up. But for now, let's keep the greenhouse the same. Now, solar panels, 30% efficient. Those solar panels that NASA launches on satellites, those are about 30, in the low 30s for percent efficiency. Those are super expensive panels. Let me do another little sidebar. This is a really interesting number. I have a lecture on the efficiency of photosynthesis and the efficiency of solar photovoltaics. Both processes follow what's called the Stark-Einstein law, which says 1 photon excites 1 electron. And I'd love being able to quote something from Einstein that I can understand 1 to 1. So 1 photon from sunlight excites 1 electron in a solar panel, and that's the first step in photosynthesis too. Photosynthesis, in theory, can get to 30% efficient, and in practice, we get into the mid-20s% efficient. But why is photovoltaics better than solar panels? Here's the reason. Here's wavelength. This is sunlight. With solar panels, we can layer panels. And if this was plants, we'd roughly be using this blue region down here. And after 700, 750 nanometers, the photons are too low energy, we can't use them, but we have solar panel coatings that can capture lower energy photons out here, and you add the colors together and you get, it beats photosynthesis because they can use lower energy photons in a solar panel. All right, 30% efficient, now we're up to 9. Now we run these through LEDs. The theoretical maximum efficiency of solar panels is about 5 micromoles per joule. Uses Planck's equation, inversely proportional to wavelength. But I don't think we're ever going to get 100% efficiency of LEDs, but I think we'll get to 90% efficient. So we're close. Now, 9 times 4 point, now we're equal. Now 1 acre of solar panels gives us 1 acre of full sunlight with electric energy. And yeah, I don't know how long it's going to take us to get there, but we're headed in this direction. Now here's another key thing. What if this is a cloudy day? Well, everything scales. The energy goes down, this goes down. It's still a 1-to-1 ratio. But if you're in plant science, do we grow lettuce indoors under full sunlight? No, we do not. 500 micromoles is plenty to grow lettuce, and that's a quarter of full sunlight. So with electricity, we can take this light and spread it out over more acres. So now we have more acres of indoor production than we have acres of solar panels, but we can't store electricity, or at least we don't have efficient ways to store electricity. So if the sun is, if it's a dark day, you want to concentrate this. If it's a sunny day, you can spread it out. Every day is different. But here's the key point. Even though we don't have cost-effective ways to store energy for the long term, there's a lot of options to store it for a period of hours, not days and weeks like an electric car, but run a pump water uphill, and then at night the water runs down, he'll do hydroelectrics. A lot of things we do to store energy for short periods of time. So now we can take those peak sunny days, store the electricity for a few hours, and have a 16-hour photo period year round with a low level of light. So that's a very key part of indoor agriculture, is distributing these photons in time to make the system maximally efficient. Right now, we just buy electricity off the grid. But if we're going to look at something sustainable, we can't do that. We've got to do it with solar panels. So this is where I can, we have a smart board for recording, and I could put black slides and do calculations on the board, but that would ruin this screen if we did that. So now I'm going to switch to calculating yield, potential yield in a controlled environment, because this is key to the whole thing. How high can yield get? And I see people all the time saying, we have no idea how high yield can get. What do you mean? We know the efficiency of photosynthesis. We can calculate that. Yet you should quit saying we have no idea. This is one of the papers very early in my career. And if you're a really old geezer, you remember Frank Salisbury's plant physiology textbook. He's one of the reasons I went to Utah to work with him as a young scientist. Exploring the Limits of Crop Productivity, 1988, published in the journal Plant Physiology. And it was this 4-component model that helps us calculate potential yield. The first, so we start with moles of photons in, and it just take a 1 up here. We assume in this case, 80% capture of light. Now, when a crop is filled in, it's probably 95% capture of light, but it always takes a while to get there. And you have to average in the low capture in the beginning with the high. This is a very high number, but lettuce can get there. High density lettuce, 80% capture of photons. If photons hit the ground or wasted. Then the next step is quantum yield, moles of carbon fixed per mole of photons. And this is a less well-known number, but with CO2 enrichment, we can get to 0.6. Now, this is heavily dependent on light intensity. The higher the light, the lower this number. But for low light lettuce, 0.06. That's a very excellent number for perfect lettuce. No problems anywhere. Then we have to multiply that by respiration efficiency of the plant. You know, we sort of go 2 steps forward in the day and 1 step back at night as the plant synthesizes proteins and other things. And this is now a well-studied number, and 60% efficiency in respiration is the widely used number. And this is successive multiplication, 0.8 times 0.06 times 0.6. Harvest index is the edible part divided by the total. And in the case of lettuce, 90%, I mean, it's incredible. It's just a tiny bit of stem base and roots. This is why lettuce is so good. You multiply those 4 together, we get moles of carbon fixed per mole of photons. And then we can multiply by the ratio of weight of the plant by carbon. That's 30 grams per mole, 0.07 grams per mole. That's another really, really useful number, but it's hard to remember 0.07. I like to remember numbers that are more like 1, like a penny per mole of photons. So let's put in potential, what we think we could get. The 80 goes to 90 with variable spacing. Maybe a little lower light, this inches up. We do cool nights to preserve carbon, 65, harvest index. Now we get to 1. So this number is what I've used in lots of models to say potential yield, if everything's just right, and it only works with lettuce or leafy greens because of this super high harvest index. Many of you may know our field crops. Harvest indexes are more like 40%. And with plant breeding, we're 45%. They're half of this number. But with lettuce, we can get to 1. So now we can do some economic analysis with this, because we're going to say we can produce a gram of dry weight per mole of photons, and the photons cost a penny per mole. So let's take a look at that. This is a paper with some colleagues We sent this to Science. They said, nah, we're not interested, but Nature took the paper. And that's pretty common to get them to even take a paper for review. Photons for physiology and food. This is the cost of the electricity divided by the value of the crop. And microgreens and lettuce, this is like a no-brainer. The electricity, 1 to 5%. Microgreens are a lot better than lettuce because they're real high water, real high harvest index, real high photon capture. But both of these are really favorable because the photons didn't cost that much. Now, let's do tomatoes. Now, tomatoes have a much lower harvest index. There's a lot of stems and leaves, we throw them away. Tomatoes are also less water. This is assuming 95% water, because that's what we sell is fresh weight. Tomatoes are less water, lower harvest index. That number jumps to 18%. So suddenly tomatoes are 4 times as hard to do as lettuce, but depending on the other costs in the system, 18% still okay. The value of the product justifies the electric bill. Now let's keep going. And you're doing strawberry research here. In this paper, I calculated this for other vegetables like broccoli. These are things with lower harvest index and higher percent dry weight. So they're harder to do economically. And I just put general vegetables, 103%. So just the cost of electricity at current value of electricity and the market value of the product, you could sell them and pay the electric bill, but no other costs. You couldn't pay air conditioning, you couldn't pay labor, nothing. Just they're equal to the cost of the electricity to grow them. The point here is that it gets rapidly harder to grow lower value, higher dry weight crops with electric lights. So if that's the case, some people say field agriculture is dead. We're going to grow wheat and rice in here. Now, wheat and rice are real low value and real high dry weight, 100 times. The cost of the electricity just to run the lights is 100 times more than the value of those crops. Unless we are really, really out of water, we are not going to be growing wheat and rice with electric lights. The economics are not even close to favorable. Doesn't keep people from promoting it and trying. And I'll say in a minute, it depends on some other factors too. So why is this so big? Market price. It goes from high to low. And then the other big factor is harvest index. Really high harvest index down to low. I showed this slide in Wageningen University. It was a couple of years ago, right before COVID, or a slide like this. And I don't know if you know Leo Marcellus. He's one of their long-standing researchers, and he jumps up and he says, I can get 70% and I can get tomatoes that are 90% water. And okay, but that means this is maybe more like 10% or something. It's still hard to grow tomatoes. So now let's look at this another way. Oh, before I get there, how about shipping? I was motivated to do an analysis of shipping costs because, man, a big truck driving from Southern California to Manhattan or to Ithaca, wow, that just has to be a massive amount of energy. This cannot be cost effective to ship it across the country. So we do some arithmetic, and I had to call up shipping companies and get data. Those big trucks only get 7 miles to the gallon, and diesel fuel is 139,000 kilojoules per gallon, 2,800 miles diagonally across the country. You multiply those numbers together. Oh, and the trucks can hold 18,000 kilograms of fresh weight, a big truck. You multiply those 4 numbers together, the units cancel. 3 kilojoules per gram fresh weight. Wow, that is a lot of energy to ship it across the country from This is a refrigerated truck, by the way, so it's even more. That's why the mileage is so bad. So how much does it cost for the electricity to grow a gram fresh mass of lettuce? Same math as before, only now 1 mole of photons, 20 grams fresh. This is 5% dry, fresh, 5% dry weight. Our very best electric lights, 14. The cost of the energy cost of the electricity is about 4 to 5 times greater than the shipping cost. This is not an intuitive thing at all, but I've shown this math to several people and they say, no, it's right. And then turns out Mother Jones magazine did an article on this some years ago. I didn't know that magazine was still around, but they're thriving. And their article was called House of Chards. And they had my calculations in there on shipping. And indoor agriculture is a wonderful thing, but don't tell me it's going to save the planet. If it'll save the planet if we can get people eating more fresh fruits and vegetables, that's a great thing. They're wonderful. And that's a huge thing. And it'll save the planet if we're out of water, but we're not going to get there on an energy basis. That's a staggering difference with the cost of shipping. Now, this slide was inspired. If you read the fine print, look at the authors on this. David de Villiers, Wayne Reed, Lou Albrecht, 2011. Energy use and yields in tomato production, field, high tunnel, and greenhouse compared to the northern tier of the USA. This is a great paper, now 10 years old. And I took the numbers from this paper and adapted them to make this graphic. And there's Lou Albrecht, who I understand is as sharp as ever just in assisted care living. But he inspired me early to do this stuff. So let's take a look at this. Grown and shipped, these are kilograms CO2 equivalent per kilogram of tomatoes. Transport 0.3 to production. So the sum of these two is 0.6 kilogram equivalents. Hoop houses, wow, they're wonderful. Now, only in season, but there's no shipping. They're wonderfully efficient, right to the consumer. Heated greenhouse, the heating's a big penalty. And the production costs are a little bit higher because very intensive fertilization and watering and care. But now look at indoor farming. The electricity cost is big. Now this is kilogram CO2 equivalents for this. So you add these numbers together to get the comparison for tomatoes. What about lettuce? This was inspired by Mike Hamm, a professor at Michigan State. This is a paper he wrote on a similar thing. Transport is more for lettuce, doesn't ship as well. You got to ship it faster, refrigerated. Hoop houses are still very efficient. Heated greenhouse, the story is similar. We just have to add in the electricity for lettuce. Now, this is not cost. This is not the economics. This is kilograms of CO2 equivalents. And if we're interested in reducing our carbon footprint, this is what matters. We got to find a way to get this number small with solar panels to make this system work. But it does say, wow, really simple things like hoop houses are wonderfully efficient, except for labor to do all this work in a hoop house. One more slide on economics. If we take the same numbers we did before, cost of electricity, efficiency of the lights, multiply them together, and we get 0.5 grams per mole from our yield model, we can grow a kilogram of dry weight of food for $24 of electricity. It's just the electricity, not anything else. So now let's look at the value of the products, starting with wheat. Organic wheat, high value wheat's about $4 a bushel, but organic wheat's 9. That comes out to 32 cents per kilogram of wheat. This number is a lot bigger than this number. It's unless something else becomes radically limiting, doesn't make sense to do wheat. How about tomatoes? This is a high-priced kind of organic, high-valued tomatoes. And they're 90% water. That's huge. $100 a kilogram. That number is bigger than that. So now, as long as it's a high-value crop and we can sell the water for fresh produce, makes sense. And tomatoes are even better. 95% water. So these two numbers exceed that. But it helps to show the challenges of different crops in indoor agriculture. Some of them make immediate economic sense and others are very challenging. Arrow Farms has been working on growing strawberries. And I'm thinking, oh, you know how hard strawberries are to grow? I mean, way harder than lettuce, not just the crop itself, but the economics. And well, they're not there yet. Strawberries are tough. I'm going to close. Yeah, how many?
About 5 or 6 minutes.
Okay, yeah, that's why I said I'm going to close. I'm watching the clock. I did just two slides left. I've done a bunch of analysis, which I'm not going to show you, but it's pretty simple. In a greenhouse, you pay for the heat and the light's free. And so what's the ratio of joules of energy per heat to photons of light? We can call this one micromoles per joule that we're getting in a greenhouse. And over here, the heat is free and we pay for the electricity, 3 micromoles per joule. So how does this compare? Not surprisingly, here's light through a season. This happens to be in Logan, Utah, but you get similar things here. Dark in the winter, here's an average. In these dark months, indoor farming clearly works because the electricity is cheaper than the sun. Here it doesn't. And I went through a bunch of calculations to see when it's cost effective. And then I had an opportunity to meet this young scientist, Luke Grams, at Wageningen. And he published this paper, Plant Factories versus Greenhouse, Comparison of Resource Use Efficiency. And to make a long story short, he said this is a no-brainer. In these polar regions, indoor farming always wins. And in the middle latitudes, it doesn't win. Now, if you're interested in this, I'd recommend his paper because it's full of equations and the details and the resources for this. One of the things he does is water in that paper. And these blue dots are where indoor agriculture makes sense because we're out of water. And it could be very efficient for water. So water and energy are the two big factors. I'll close on one slide. The biggest advantage of indoor ag to me is it can be very automated. Shelves of plants, the labor bill goes way down and we're having trouble getting labor for agriculture. The biggest disadvantage is electricity. So now it works because this cost goes down and this cost goes up and we're at least on the threshold of doing this economically, for sure for lettuce and microgreens. But it's going to be a while before we get there with some of the other crops. Even crops like broccoli is just much harder. So I'm going to stop there and take questions.
We don't have anything from Geneva at the moment. Anybody? Any questions here?
Can you go back to the economic slide, couple slides before? Was it 24 cost of electricity?
This one right here?
No, the economics. Yeah, right there. I'm just curious what that 24 is. Is that for that factory? Or?
This one right here? Yep. No, this is just the cost of electricity. Well, this is the cost of electricity right here per mole of photons. This is from the yield model. And now I just said lettuce, we could get 0.7. So, but this is for dry weight, not fresh weight.
Okay.
And this is this would be a very high yield for field crops. Field crops, you get to 0.3 maybe grams per mole. This is a high estimate for yield. So I've kind of, it's at least $24 per kilogram and maybe more like 50. But I wanted to make this number as small as possible so people couldn't say I was rounding the numbers in my favor. But that's where it comes from. Cost of electricity times yield per photon.
So the growth depends in any settings.
It's for anything. Yeah.
Next.
Yes.
Has anybody done these calculations per calorie produced? Because lettuce and tomatoes hold dressing, but
Yeah.
don't
Sure.
really
Sure they have.
get you.
And all of us in horticulture look really pretty bad when we do calories because we
Yeah.
got pomology, which, apples and oranges and agronomy. The favorite motto in agronomy is agronomy feeds the world, right? And yeah, well, horticulture makes the world healthy.
Okay.
But none of this looks very good for calories. You have to have, wheat and rice are the two staple crops in the world. They're similar in terms of human consumption. And oh my, I think something like 80% of the world calories comes from either wheat or rice.
Yeah.
So those, if you gotta do those to feed the world. Corn and soybeans are fed to pigs, almost always, at least now in the commercial approach. Yes.
So I noticed that you were focusing a lot on solar energy. I was wondering if you did any calculations with wind energy or geothermal.
I have not, but we could.
I'm sorry, what was the question again?
So could we do this with wind energy? And it's similar challenges. I mean, wind energy is so localized, when you fly across the country and you can see a bunch of windmills and nothing. Wind energy is more challenging than solar because it's so non-uniformly distributed. A few places with high wind, and we're working hard to mine those places. Where solar is, what's the number? More solar energy falls on the planet in an hour than the whole population uses in a year. I mean, we have abundant solar energy. We just got to figure out how to use it. So the reason I didn't do wind is because it's less available and it's generally less favorable economics. But in the places with high wind, then it works. Yes. Neil.
Question along those lines. So I'll push it a little bit further. What about nuclear or then like nuclear fusion?
Sure. And if we could get nuclear fusion, wow. Now this whole thing makes sense immediately. But if we got nuclear fusion, all kinds of things would change. Gas-powered cars would become old-fashioned overnight. So it depends. So when you think about big picture energy, depends on how we can get electricity. People.
So what exactly are the benefits outside of reduced labor costs of automation? Like, are there benefits other than like economic reasons for reduced labor costs?
Can you repeat the question, please?
Are there benefits other than reduced labor?
Right, so, you said like improved automation is like the main benefit.
No, high quality food is a huge benefit.
Okay,
Very fresh. Honestly, I think we would get people eating more vegetables if they were high enough quality. But right now you go to the store and only the wealthy people can afford those, and the people that need them the most are the underserved people. And we're not going to get to those people when it's $4 per pound of lettuce or tomatoes. They're buying the cheapest stuff they can get. But that's a huge benefit to higher quality produce.
okay, but like one thing of indoor ag is like you said, increased automation, right? That was like the last slide. Is there like, that is like a benefit because it reduces the labor costs, but is there any other benefits?
Well, yes, as I mentioned, savings of water, that's for sure. We can also say savings of fertilizer, because if we do it right, we can recycle the fertilizer too. Doesn't go into the groundwater. We're going to run out of phosphorus at some point. And so a system like this can be more fertilizer efficient because it's very controlled.
Yeah.
So
Sensing and data acquisition and managing consistently with
Yeah.
automation.
yes, it lends itself to a lot of technology. I mean, I'm super excited about it because that's what we do, controlled environment agriculture, high input, high output. But I guess the point is it's got farther to go than most people like to admit for lower value crops.
Okay, well, let's thank Dr. Bugbee.
This has been a production of Cornell University, on the web at cornell.edu.